Strings are one of the most common data types in R and typically consist of a sequence of characters, which can be letters, numbers, punctuation, and even whitespace. Now, the ability to manipulate strings is a vital skill for data scientists such as yourself. Tasks like cleaning messy data or formatting outputs heavily rely on the ability to parse, combine, and modify character strings. In this lesson, we'll focus on techniques for working with character strings in R using the stringr package from the Tidyverse. Let's get started. On your screen, you'll see a list of our learning objectives for this lesson. If you like, you can take a second, pause, and read through them, but we'll also go over them at the end. To get started, let's load in the packages that we'll need. With Pacman, we're going to call in the Tidyverse, which includes the stringr package we're mainly focusing on today, the here package, and janitor. So before diving right in, let's first define strings. Now, there are fundamental rules for defining character strings in R. Strings can be enclosed in either single or double quotes. However, the type of quotation mark used at the start must match the one used at the end. So, for example, if you start with a double quote, you must also end with a double quote. And vice versa, if you begin with a single quote, you must also end with a single quote. So, for example, if you run this code chunk, it's fine. It is able to run, it's valid. Now, another rule to keep in mind is that you normally cannot include double quotes inside a string that already starts and ends with double quotes. Now, the same applies vice versa to single quotes inside a string that start and end with single quotes. So, for example, if you take this code chunk wherein we have one string that start and end with double quotes, and it also has double quotes inside, and we have one string that begins and ends with a single quote containing a single quote inside, when you run this, you get an error. However, mixing single quotes inside double quotes and vice versa is indeed allowed. So if we pay attention to our small example here, notice that our string now begins with double quotes and ends in double quotes. It contains a single quote inside. And this, in fact, is allowed. And when we run that code chunk, we see that it was successful and no errors were given. Alternatively, we can also use the escape character, which is a backslash, to include a literal single or double quote inside a string. So this is what we call an escape. In order to adhere to the rules that we've stated above, if you would like to include single quotes inside single quotes, so this is the single quote within the single quotes, you can do so with this escape. And the same thing for double quotes. If you would like to include double quotes inside double quotes, we'd simply indicate this escape character here. So if we run that, it's successful because we have this escape, which is comparable to these strings wherein we tried to run them, but this was not valid because it did violate the double quotes inside a string starting and ending with double quotes. You may have noticed that when we ran the previous code chunks, we did not have any outputs displayed. Well, to display the strings we created as they would appear in the output, such as a plot, we can use the cat function. So if we run this line, we can see now the single quote which would appear here. This was the sentence that we created up above. And if we run the double quote string that we created, we would have the following. Double quotes inside double quotes, which is once again the string that we created previously. So as you can see, the syntax for the cat function is relatively straightforward. You have a single argument of the function, and cat simply prints its arguments without additional formatting. As a side note, since the backslash is already an escape character, you must use 2 backslashes to include a literal backslash in a string. So if you would like to include a backslash as we're creating in this string, we need to include 2 of them. if we run that, only one backslash shows up within the string that we created. The first one was merely an escape character. So to test that once again, if you only include one backslash, it's an incomplete expression. So you receive an error in that case. So I'll just add back the second backslash in order to properly create that string. At this point, let's take the opportunity for a small practice question. Take the time, pause, and write down your answers. Now that you know the basics of strings, we can finally start learning how to format with stringr. Now, the stringr package in R provides useful functions for analysis and visualization. This includes case changes, whitespace handling, length standardization, and text wrapping. Let's first go over the first point, which is changing cases. Now, converting cases are often needed to standardize strings to prepare them for display. And the stringr package provides several case-changing functions, one of which is the string to upper function, which converts strings to uppercase. Now, if we look at our small example, in the string to upper function, we have a simple string that we've inputted, which is hello world in all lowercase. Now, if we run that to see, the string to upper function converts the lowercase letters into uppercase. Alternatively, stringr also contains the string to lower function, which converts strings to lowercase. Here, we've specified a string that begins with an uppercase letter, and if we feed that into the string to lower function, we can see that it has now been changed into a lowercase letter with goodbye starting with a lowercase g. And finally, the string to title function capitalizes the first letter of each word, which is ideal for title names, subjects, and proper nouns alike. And once again, within our simple string to title function, we've indicated a simple string that is in lowercase. All of the letters are small. And if we run that, we see that the first letters of each word have now been capitalized. Now, the second point that we saw up above was that R has some packages which allow us to handle white spaces. Now, managing white spaces makes strings more neat and uniform. And once again, the stringr package provides two main functions for this, one of which is the string trim function, which removes leading and trailing whitespace. Leading just means before the string, and trailing means after the string, which we see in these spaces. This is leading whitespace in the beginning of the string, and this is trailing whitespace at the end of the string. So if we feed this string into the string trim function, we're going to get a trimmed string wherein you no longer have white space before or after your string. Now, additionally, the stringr package also contains the string squish function, which, similar to the string trim function, also removes white spaces at the start and end, but it also reduces multiple internal spaces to one. So it will take out the white spaces in between your characters. So in this case, if we run the string squish function, just this simple line, we see that the space in the beginning and the end have been taken out, and also the spaces in between the characters have been reduced to a single space. So it had reduced multiple internal spaces into one. And this can be comparable with the string trim function we just went over. So if we feed the same string into the string trim function, we see that the beginning and end white spaces were deleted, but the internal white spaces were kept. Another function that we would like to introduce is the string pad function, which pads strings to a fixed width, and what it essentially does is help standardize the length of strings by adding characters. So to see this function in action, let's take, for example, that we would like to pad the number 7 to the left with a total width of 3 using 0. So within the string pad function, our first argument is going to be our string to pad, which in this case, we said we would like the number 7. The second argument we'll indicate is width. So we said we would like a total character width of 3 with the addition of a 0 pad. So once we run that, we see that we have successfully padded the number 7 on the left with zeros for a total of 3 characters. To reiterate, the width argument sets the final string width, so the total number of characters we have, and pad specifies the padding character. Here we inputted 0, which is why we have zeros appearing in the left of 7. Now, the side argument, which we didn't necessarily specify within this string pad function, you can input left, right, or both. But the side argument defaults to left, so padding will be added on the left side if it's not specified, as what happened here in this function. But if we would like to pad on the right side, we can also do that. Once again, if we would like to pad the number 7, now with a total width of 4 to the right side with a different padding, so instead of 0, we've indicated an underscore here. If we run that, now we see that the number 7 has 1, 2, 3 underscores to the right of it, because we specified a padding to the right with the underscores, and it's a total character length of 4. So we have 7 as 1, and the remaining underscores, the remaining 3 underscores as the 4 other characters. And lastly, we can also see how that will go for padding both sides. So if we would like to pad both sides, once again with the number 7, our first argument is the string we would like to pad. Here, we want a total width of 5, so a character length of 5. And we would like to pad it on the both sides. And we would like to pad it with an underscore as we did up above here. So, as we can see, we've successfully padded the number 7 with an underscore on both sides. And if we count them, we have a total of 1, 2, 3, 4, 5 characters. So we have a string with a length of 5 characters. Moving forward, the string wrap function wraps text to a set width, and this is helpful to fit strings into confined places like plot titles within your ggplots. So, for example, to see this function in action, we'll create this long string. And now, if we want to wrap this text into 10 characters, we can write within the string function the example string that we created as the first argument and the width as 10 because we want it wrapped to 10. So we run that and we run the last line, we have the following output. Now this may be confusing with the many backslashes, but the \n that you see in between the characters simply indicate a line break. To view the modified wrapped to 10 string properly, we can employ the cat function which we previously saw. And within this function, we're simply going to paste in our wrapped to 10 string. And here we can notice that the function maintains whole words. So it won't split longer words like manipulation. Alternatively, setting the width to 1 also splits the string into individual words. So if we run that, we can see that within the string wrap function, we can split them into individual words. As we've said, the string wrap function is particularly useful in plotting with ggplot2. So for example, we can theoretically employ the string wrap function to prevent this long title that we've created from spilling over in a plot. So if we run this line and also visualize this plot, we see that since the title is very long, it is no longer visible and spills over the plot. However, if we use the string wrap function within our ggplot code, we can indicate the long title string that we've created with a width of 50. So if we run this plot, we see now that the title is all visible and fits within the plot. So in essence, string wrap keeps titles neatly within your visualizations. With that being said, it's time for some practice questions. First, we'd like you to practice cleaning data by trimming white spaces and converting each name to title case for consistency. Then we want you to practice some padding, so your padding skills. And last, we would like you to employ the string wrap function that we just used for our plots in order to format this long title properly. So take a second, pause, and write down your answers in your own RMD file. Let's apply the stringr package's string formatting functions to clean and standardize dataset. In this case, our focus is on a data from a study on HIV care and treatment services in Mozambique. The original dataset itself already had various formatting inconsistencies, but we've also added additional mistakes for educational purposes. So first, with this line of code, we'll load the dataset. And in the second part that you see here, we'll select for the 4 variables which had formatting issues. And those are district, health unit, education, and regimen. So let's load that. And as you see, we have 1,413 rows and 4 columns, which correspond to the 4 variables that we just selected for. So using the table function, we can identify and count the unique values to reveal inconsistencies within the dataset. So using our quote-unquote messy dataset, we can feed in our corresponding variables into the table function. So we did that for each of the 4 variables that we have. And once we run that, we have the output. Now this following output, as we said, reveals the inconsistencies within the dataset. However, as you can see, it's not very intuitive and it's actually hard to interpret the differences in this case. Another useful function for visualizing these issues is the table summary function from the GT summary package. With our messy data and the selected columns that we have, we can simply pipe in our table summary function. And from there, the output clearly shows inconsistencies in casing and spacing formats. So, for example, within the education column, we see that primary is spelled with an lowercase p and an uppercase p, as well as for secondary. You can take the time and identify the inconsistencies within the variables from this table. Next, we need to address the issues that we see here systematically. In order to do that, we need to clean the dataset. So we're going to create a clean dataset from our messy with mutate and the various stringr functions that we learned earlier on the lesson. So for the district column, we're going to standardize the district names with the string to title and string trim functions. So we're just going to input district. For the health unit column, we're going to remove extra spaces with the string squish function. And finally, for the education and regimen columns, we're going to standardize them with the string to title and string to upper functions. So once we've inputted that, we can go ahead and run the code chunk. Now, if you need a reminder of what these various stringr package functions do, feel free to rewind the video wherein we discuss each and every one of the functions and show how they work in action. In the meantime, we can verify the effectiveness of the changes that we just made by rerunning the table summary function once again. So in this case, we can see that it was successful. Taking again the education column as an example, we see that primary has now been consolidated into this one primary category that is written with an uppercase P, and the same goes for secondary. Now feel free to check for all of the components for each column. Now that's done, we can finally attempt to plot counts of the health unit variable. However, when we run this code chunk, we can see that there is an issue with lengthy labels. To resolve this, we can simply adjust the labels using the string wrap function. So using the clean dataset, our HIV clean dataset, in our ggplot code, we're simply going to input string wrap and input the column that we used previously, which is health unit. And for width, we're just going to specify it with a larger value of 20. Now we can see that the labels have been wrapped around and no longer run into each other as we previously saw. Although this is much cleaner, we should probably fix the axes title, which simply states string wrap, the variable, and the width. So to do that, we can simply, within our ggplot code that we just specified above, we can simply add a labs argument and give the bar plot an appropriate x-axis title. So there you have it. We have a much cleaner and readable bar graph with an appropriate x-axis title and labels that do not run into each other. Now it's time to try your hand on similar cleaning operations in the practice questions below. So take your time, pause your screen, and answer. Moving forward, let's go over splitting strings, which is a common task in data manipulation. The tidyverse offers efficient functions for this task, most notably the string split and separate functions. Now, as we said before, the string split function is useful for dividing strings into parts. To see this function in action, let's take this example string into consideration. So if we run that to create the string itself and want to split it with a string split function, in the first argument, we'll specify the string name first, so example string. And in the second argument, we'll input the pattern where the split should occur. In this case, since our string is separated by hyphens, as you see here, we're going to input the pattern to be split at the hyphens. So when you run that, you see that this specific code splits our example string at each hyphen, resulting in 3 separate strings. However, applying the string split function directly to data frames is a more complex process as opposed to simply applying it to one string itself. To see this, let's try it with the IRS dataset from Malawi as a case study. Now, you should already be familiar with this dataset from a previous lesson, in case it is available in the hyperlink on your lesson notes. So once we run this code chunk and load our IRS dataset, you see that we've loaded specifically the village and the start date long columns. But for the purposes of this example, we'll mainly focus on the start date long column. Suppose that we want to split the start date long variable to extract the day, month, and year. Within our string split function, we'll specify as a first argument, as we said, the variable that we would like to be split. And in the second argument, we're going to indicate the pattern where the split should occur. Now, if we scroll back up and look at the original format of the start date long column, we can see that the components of month, day, and year are separated by spaces. So within our pattern argument in the string split function, we'll simply indicate a space. And when we run that, we see that this results in a list column, which can be difficult to work with. So to make it more readable, we can use instead the unnest wider function. So within the string split, we'll here again indicate the space, which is the pattern where the split should occur. And within the unnest wider function, in the first argument, we'll put the column where the splits are located. Here it's called start date parts, So we've inputted that here. And for the second argument, it's going to be our name sep argument, which basically just specifies how the new columns should be named. And here we'll indicate an underscore, because generally we do recommend you to name your columns with underscores. So running that, you can see that it works extremely well. Our dates have now been split into 3 different components. We have our month column, our date column, and our year column. However, while this does work well, the code is quite cumbersome. A better solution for splitting the start date long column into different components would be the separate function. As we just mentioned, the separate function is much more straightforward for splitting strings. To see this in action, let's try the same tasks that we just performed with the string split and unnest wider functions with the separate function. Here, we've already pre-filled out the code, but once we run this code chunk and look at the output more closely, we'll explain the syntax. Once we run that code chunk, here it's been abbreviated by R, but if we click on this tiny icon, we have the resulting output, and we can see that the code that we've provided above with the separate function is much more straightforward, and we get the separate components that we've wanted, which was month, day, and year. Now, let's review the syntax more closely. So with the separate function, all you need to specify is first the column to be split, which in this case is the start date long column, the into argument, where we have also the create function. We're going to specify the names of the new columns that we would like created, which are month, day, and year. And last, the sep argument, which specifies the separator character for our start date long column. And as we previously went over, in this column, the components are separated by a blank space. However, if you see, once again, it's hard to see with the R abbreviated version, but in this small output that we can look at more closely, within the new IRS dates 1 dataset, our original column of the start date long variable is now gone. However, to retain the original column, within our separate function, we can simply add another argument after our sep argument, which here is going to be remove. And once again, to retain the original column, we're going to set the remove argument to false. And running that code chunk, we can see in our output that the start date long column has been retained, and our month, day, and year columns, which are our new columns, are also visible. One thing to look out for is that when some rows in your dataset lack all the necessary parts, or if there are NAs in some of your rows, separate will issue a warning. Now we can demonstrate this by artificially removing all instances of the word April from our database with the following code. So within our replace function, we're going to artificially remove all instances of April from our dates. If you look at these 2 rows, you can see that we were successful because the month April is now missing from these 2 entries. From there, we can now try to split the date parts into its 3 different components of month, day, and year. And as you can see, the row's missing parts will produce warning messages, as we've said. And we do implore you to handle these warnings carefully, as they can lead to inaccurate data. In our case, when we take a closer look at the output, we now have the day and month information in the wrong column. And instead of having our NAs in month, the entries for year are now the ones with NA values. For now, let's take a small break and try out a practice question. Considering the esophageal cancer dataset, we would like you to split the age ranges in the age group column into two separate columns, age group lower and age group upper. Note that after using the separate function, the 75 plus age group will require a special handling. Use now the parse number function from the readr package or another method to convert the lower age limit of 75 plus to a number. Take a moment, pause your screen, read, and write down your answer. Now, to use the separate function on special characters like period, plus an asterisk or a question mark, we need to escape them with double backslashes. To see why, let's consider a scenario where the dates in our IRS dataset are formatted with periods instead. So running that code chunk, you see that now the start date long column is formatted with periods separating the character strings. If you attempt to separate this date format directly with a sep argument as before, so in this argument, we'll simply state a period. It does not work. You have columns, even though they've been abbreviated by R, this stands for date, month, and year. So you have columns that are empty, and it doesn't work as intended because in regex or regular expressions, the period is a special character. Now we'll learn more about regular expressions in future lessons, but the main thing to focus now is the correct approach to separate these strings, which is using the double backslash. So instead of simply inputting the period, in this case, we'll indicate a double backslash alongside our period. And here, now the function understands to split the string at each literal period. And if we look at the output more closely, we see now that it's been split correctly into the three different components of day, month, and year. To reiterate, when using other special characters that we've mentioned like asterisk or question marks, they need to be preceded with a double backslash in the sep argument. So if you're wondering what special characters are, well, in regular expressions, they help us find patterns in texts, and special characters have specific roles, as we said, like the period. Now, we are not going to cover this in depth at this point. However, feel free to look over resources in R. Otherwise, more on these special characters will be covered in future lessons. At this point, it's time for a small practice question. So in this question, your particular task involves the HIV data clean 1 set. And the focus is going to be on the regimen column, which lists drug regimens separated by a plus sign. Now, your goal is to split this column into 3 new columns using the separate function. So as we just went over, pay close attention to how you handle the plus separator. Take a moment, pause your screen, read the question, and write down your answer. Another useful skill to know is how to combine strings in R. Now, the paste function in R concatenates or joins together character strings, which allows you to combine multiple strings into a single string. To see this, let's combine our first string, hello, with our second string, world. So if we paste these strings together, strings 1 and 2, we receive one string which reads hello world. The default separator in this case is a space, so it returns hello world with a space in between the strings. Let's now demonstrate how to use this on a real-world dataset using the IRS date data. We'll we'll first separate the start date into individual columns. So with the separate function that we just went over, we'll use the start date long column to separate them into the month, day, and year components, keeping in mind that the characters are separated by spaces, and we would like to conserve the original start date long column in the new dataset that we create. So once we do that, we can see that we've conserved the original start date long column and also have the month, day, and year components. So if we want now to combine the day, month, and year, we can do so with the paste function. So within paste, we can input the various strings that we would like to concatenate or join together. We would like to have the day, month, and year recombined. So when we run that, we have in our start date long 2 now our 3 different components combined. Furthermore, the sep argument specifies the separator between elements. So in this case, the separator is a space. But for a different separator like a hyphen, we can write in the paste function. So before we specify day, month, and year. Now, if we want a different separator other than a space, we can input in the sep argument a hyphen. And once we run that, you can see in our start date long 2 column that the different components are now separated with hyphens instead of spaces that you see up above here. To concatenate without spaces, we can simply set the sep argument to 2 double quotes without any characters or spaces in between them. So just plain double quotes. Within the paste function, we'll once again write the 3 components that we would like pasted together, which are day, month, and year. And in the sep argument, we're going to put our 2 double quotes. And here we see with our start date long 2 column, we have all 3 components pasted together without spaces. Alternatively, we can also use the paste 0 function, which is equivalent to this paste function wherein we specified in the sep argument to concatenate the different components without spaces. So in our paste 0 function, we're simply going to indicate the 3 components we would like pasted together, which are day, month, and year. And when we run that, we can see that the output is the same. So in our start date long 2 column, we have all 3 components of day, month, and year pasted together without spaces, as what happened when we used the paste function specifying the separator argument. So it's the same output that we got. It's just the paste 0 function is much simpler when you would like to concatenate without spaces. Moving forward, let's try to combine the paste function with some other string functions to solve a realistic data problem. So considering the ID column in the HIV data MESI 1 dataset, as you see here, we would like to standardize these IDs to the same number of characters. This is often a requirement for IDs. So to implement this, we can use the separate function to split the IDs into parts, as you see here, separate function. And then finally, we'll use the paste function to recombine them into a standardized format. To do this within our separate function, we'll specify the different columns that we would like to separate the patient ID into. We would like to create one column that contains the prefix of the patient ID numbers and another column which contains the actual patient number. We would like them to be separated with a hyphen, and we're going to keep the original patient ID column in this case. And in the paste function, we're going to specify the prefix and patient number columns that we created here to be pasted together. And once again, we would like them to be separated with a hyphen. And once we run that, we see that we were successful in creating a new patient ID column wherein we standardized the IDs to have the same number of characters. So how did we do that? Well, we did that with the string pad function here. So to get a full overview of how we accomplished this, well, let's review from the beginning once again. So in this example, the patient ID is split using the separate function into a prefix and patient number column. And then we piped that into the string pad function, wherein the patient number column is padded with zeros to ensure that all patient numbers are the same character width of 5. And finally, we concatenated them back together using the paste function, wherein the prefix and now the padded patient numbers are joined together and separated with a hyphen, as we can confirm in the following output. Now it's time for 2 practice exercises. First, using the Lima Messy 1 datasets, notice that the IDs are not zero padded. So your task now is to separate the ID into parts, pad the numeric part for standardization, recombine the parts using the paste function, and then resort the IDs in descending order. So as a little check, the highest ID you should have must end in 2, 3, 4, 7. The second practice question we would like for you to try out is to create a summary statement. So first, you need to create a column containing summary statements combining village, start date default, and the coverage percentage from the IRS dataset. And this statement should describe the spray coverage for each village. And we have given you a small example of how your output should look like. Now, your task is to select the necessary columns from the IRS dataset and use the paste function to create the summary statement similar to the one here. Now take a moment, pause your screen, read through the questions carefully, and then write your answer in your own RMD file. Finally, a last function that you should be familiar with is the string subfunction. Now, the string subfunction allows you to extract parts of a string based on character positions. The basic syntax for the string subfunction is first the string, the start and end position of the strings that you would like to extract. If it doesn't make sense at this point, that's okay, don't worry. Let's look at it using an example. So if we would like to extract the first 2 characters from patient IDs, which we'll create here, within the string subfunction, as we said, we'll input the string that we would like to extract from. And in the second and third arguments, we'll specify 1 and 2 because we want to extract the first 2 characters from patient IDs. And when we run that, we get the following output, ID. And if you look closely at the strings we've specified, the first 2 characters is indeed I and D for this patient, I and D for that patient. Alternatively, if we want to extract other characters like the first 5 characters from patient ID from patient IDs, we can just adjust the start and end values. So again, the first 5. So we want from the first character to the 5th character. And we'll get the following output, ID 1, 2, 3 and ID 6, 7, 8. And if you refer back to the strings we created, that is indeed the first 5 characters, ID 1, 2, 3 and ID 6, 7, 8. Now, negative values in the second and third arguments tell the string subfunction to count backward from the end of the string. And it's really useful for extracting suffixes. To see this in action, let's take, for example, the last 4 characters of patient IDs. So in the second and third arguments, we'll specify from 4, and the last one is 1. And this will return A, B, C, and D, E, F with the hyphens included. And once again, if we refer back to the strings that we created, counting backwards from the end of the string, so 1, 2, 3, 4, and it's indeed that output. And then for the second string, it's 1, 2, 3, 4. It's the ABC hyphen output. Furthermore, when indices are outside the string length, the string subfunction handles it gracefully without any errors. So let's say we want to extract from 1 to 11. We get the full output or the full patient ID that we created, even though it does exceed the total amount of characters that we have in our original string. And if we go even further, if we say we want to extract 1 through 30, we still don't get an error, and we simply have the whole patient ID as we've inputted into our string. Moving forward, in a data frame, we can use the string subfunction within mutate. So for example, we can extract the year and month from the start date default column and create a new column called year month. So to do so, we'll select the start date default column, and we're going to mutate that into a new column called year month. And within the string subfunction, we'll input, once again, start date default, starting from the first character and ending at the 7th character. And here in the output, we see that we were successful in that we've extracted from the start date default column only the year and the month, creating the year-month column. So we have our year and our month, and the day has been left out. Now finally, we've come to our last practice question. Using the string subfunction, we want you to isolate just the numeric part of the patient ID column in the HIV data MESI 1 dataset. Take your time, pause your screen, read the question, and then answer in your own RMD file. And that actually brings us to the end of our lesson. Let's now take a moment to review the learning objectives that we introduced earlier on. At this point in time, you should understand the concept of strings and rules for defining them in R. You should also know how to use escapes to include special characters like quotes within strings, and know how to employ stringr functions to format strings. This include knowing how to standardize cases with the string to lower, to upper, and to title functions, trimming white spaces with the string trim and squish functions, knowing how to pad strings to equal width with string pad, and knowing how to wrap text to a certain width using string wrap. Additionally, we further went over how to split strings into parts using string split and separate. And from there, we learned how to combine strings together with paste and paste zero. And last but not least, we learned how to extract substrings from strings using the string sub function. We'd like to congratulate you on reaching the end of this lesson. You've learned about strings in R and the various functions to manipulate them effectively. While we did cover a lot of material, remember that it's not necessary to memorize all of these functions. Just knowing that they exist and knowing how to look them up with various tools like Google is more than enough for practical application. However, we did provide you with a quick summary table at the end of your lesson notes for your own review. With that being said, that's it for today, and we'll see you in the next lesson.